Please join me in warmly welcoming Dr. Prateek Bansal. Prateek is a presidential young professor that is like an assistant professor at the National University of Singapore. Before NUS, he was at Imperial College London and earned his Ph.D. from Cornell, MSc from UT Austin, and BTech from IIT Delhi. Prateek leads the Behavioral and Cognitive Science Lab at NUS, where he researches new methods for mobility behavior and adoption of emerging technologies. He's an associate editor at the Journal of Transport Economics and Policy and the Journal of Public Transportation, and an ed board member at Transportation Research Parts A and B, and at the Journal of Choice Modeling. Welcome, Prateek.
Thanks, John. Thanks for the introduction, Don. So today I'm going to talk about new methods at the intersection of the cognitive psychology and the behavior modeling. Okay? I'll try to be less mathematical, but try to give you more intuition of what we are trying to achieve by combining the cognitive psychology and the behavioral modeling. Okay? So this is the joint work with the research fellows in our group. Eugene was the formal research fellow who joined Arju University as an assistant professor. Sorry, my voice is a bit low because I'm not habitual of cold, being in Singapore, certainly. And two PhD students, Jiazwan and Zinwei, and Vladimir is a neuroscientist in our lab who helps us in processing the eye tracking and the brain data. So what I'm going to do today is I'm going to convince you that why should we adopt models from cognitive psychology, and give you an intuition of what is the mathematical formulation. We'll not go into too much detail, but we'll give you an idea of what is the underlying mathematical formulation of the models from cognitive psychology and how they are different from traditional discrete choice models. But okay, if they are so awesome, why have not they been used so far in discrete choice? So we are going to talk about the issues in the models from cognitive psychology as well. And finally, I'm going to spend more time how we are addressing those challenges that I highlight in the third point. Okay? So let's get started. So we know that the utility-based models that we have, the discrete choice models, multinomial logic model that I think almost all of you are familiar, they're quite static. They focus on the choice that you make in the end, but it is difficult to handle that if, let's say, you have an information about how people are processing the whole information during the decision-making process. It is very difficult to incorporate that information in those random utility models. Even if you have the response time information, it is difficult to incorporate in the traditional RUM or random utility-based models. So we don't know how to account, even if we have these new data sets about eye tracking, brain data, how do we incorporate these data sets in the behavioral models? That's very difficult to do in the utility-based framework. And the third point, which is very important, is about the various marketing strategies which are there in the market. It is difficult to understand or explain their effects on the preferences of the people using the utility-based models. So just to give you an illustration of what these decoy effects really mean, you might have gone to Starbucks and let's say there's this, you have the small coffee and the large coffee, but you also have the medium coffee most of the time, right? In most, not only Starbucks, but in other chains as well. So the medium coffee generally have slightly lower price than your large coffee, but the quantity difference is significant, right? So these companies do not want you to buy the medium coffee, but the medium coffee is there so that the large coffee looks more attractive, right? So this decoy, this medium coffee can be seen as an attraction decoy. It's a kind of a decoy which helps in making this target more attractive, okay? Finding the effect of this decoy on the preference shifts is not so easy with the utility-based models, and that's the reason we focus on the models from cognitive psychology, which we call the sequential sampling models, okay? So the idea of sequential sampling models is, let's say there are two alternatives. On the x-axis you have the time. On the y-axis you have the sort of an evidence accumulation process. And let's say the participants start looking at the choice situation or an experiment at this moment. There is some time that participant loses before they start thinking about processing the information, which is the non-decision time. Once they start processing the information, they start getting information about they start accumulating the evidence about each of the alternative on the specific attributes by comparing them. And this process of evidence accumulation is defined the rate of accumulating that evidence. This is what we call the drift rate, right? And what these models assume that each of these alternatives, this is a binary choice situation, so that's why you have only two evidence accumulation lines. And what we assume that they have two thresholds. Each alternative has its own threshold. Whichever alternative reaches to the threshold first, that alternative is chosen by the respondent, okay? So you can already see that if you think about the main parameters of this model, drift rate is the speed at which the respondent is accumulating the evidence for each of the alternative. Decision threshold is basically the time at which the respondent makes the decision. And the starting point can be different as well, because I may have a higher preference for one alternative over the another alternative, and there is a non-decision time. Right? So these are the four alternatives. Now you can parameterize these four processes differently, and you can come up with the many different models. Right? So coming up with the different models just about putting the structure on this 4 different parameters that you have. Okay? So there are many models which have come in cognitive psychology. One is multi-alternative decision field theory, which is quite popular, which has been used in transportation application recently. Second is MLBA, which is multi-attribute linear ballistic accumulator model. What is the main difference between these two? These models are how they are accumulating evidence. That process is different in all these models. So you can define your own evidence accumulation process, and you can come up with a new model, basically. And the recent one is the multi-alternative decision by sampling. I'll briefly talk about the main ideas of the MLBA and the MDBS. But what is the main advantage of these models? So if you think about the main advantages, if you look at their formulation, it is already dynamic in the sense that they are accounting for the process of accumulating evidence. So they can handle the process data that we collect. If it is an eye tracking data or if it is a brain data, we can incorporate that data into these models. The second aspect is the cognitive underpinning. In psychology, people have demonstrated that these models can, the process that we assume is aligned with how people think about the decision making. And psychologists argue that these models can explain the effect of the decoy better compared to the traditional RUM models. Okay. So before I get into the issues with these models, let's look at the MLBA and MDBS to just understand how do these models in the end look like. So if you look at the MLBA model, it is a model which is nice because it has a closed form probability distribution of the joint choice and the response time. That's the beauty of it, because it assumes the drift rate to be more linear. So it makes some assumptions on the drift rate, which helps in achieving the closed form expression for the choice and response time. So what you have here is the starting point, 0 to A. So starting point can be somewhere between this range. And you have the I0 as the drift rate mean constant, and tau I is the alternative specific constant. So the main idea is, if you look at the choice probability in the MLBA, it is the probability of choice at the response time t is when the alternative I has reached the threshold, but all other alternative has not reached their own threshold. This is basically 1 minus CDF of all other alternatives, not I. Okay? So based on this, this joint distribution, and assuming once we have this joint distribution, we define this probability density function through some parameterization. I'll not go into the details how we come up with this FIT, but the main important part in this FIT is the drift rate DI. So we assume again the functional form on the DI, which is the drift rate, is the evidence accumulation rate for each alternative. And you can see this DI has a very similar flavor as of the utility equation, right? DI has the xik and xjk are the attributes, so it's the difference in attributes, and beta k is the parameter. But at the same time, you will see that there are a lot of attribute and alternative comparisons are accounted while we define the DI. Okay, so this is just a general idea how these models really look like. The second model, which is MDBS, what MDBS assume that the respondent do the pairwise comparison of alternative on each attribute at each time step and gain one evidence in the favor of the alternative in each step. And this is how generally the evidence accumulation process looks like for different alternatives in the MDBS. So the main idea of MDBS is they define at each time step, because they split the whole response time into multiple time steps. So at each time step, they say that the probability of getting one unit evidence in favor of alternative I in time step by respondent N is basically probability of alternative I evaluating that alternative I on attribute K times that the alternative I wins the comparison on the attribute K. So it's more like, first you have to figure out that how that alternative is evaluated with the other attribute. So you can think if you look at this part, probability of evaluating alternative I on attribute K, you can calibrate this part from the eye tracking data, right? Because how respondent is evaluating the alternatives on a different attribute, you can bring the eye tracking data at this part, and this part you can develop some choice model on winning, the probability of winning that alternative eye on that specific attribute comparison. So as of now, if you don't have eye tracking data, they compute the probability of evaluating alternative eye on attribute K depending on the distance of the attributes, okay? And the probability of winning the comparison has a very similar flavor of the logistic regression, okay? So the main idea is it has the two parts. One is the information search process, and second is the evaluation. And that's what makes these models different than the random utility maximization models. Okay, if they are so interesting, they have dynamic processes, why these models are not used in discrete choice, in the behavioral modeling community or discrete choice modeling. So the first issue with all the psychology-based models, they use these models in the lab-based data, okay? So they invite students and let them do the experiment and then validate their models, right? So those models are not so interesting. Those data sets are not so interesting, and that's the reason people don't rely on the results. And that's why economists don't use them so much. The second issue is, why do we need the response time? How the response time is useful, that is also not very clear in the literature. What do we gain if we incorporate the choice and response time together? We don't know yet. So what is the real value of the response time? We are going to see that as well. And the third is, okay, we can incorporate the neurophysiological data, or you can say eye tracking and brain data in these models, but how easy it is? Because this is a high dimensional data. If you look at the eye tracking data, and the brain data is also a quite high dimension data. And the lab data sets that you have, they have very small sample sizes. Okay? So there are many challenges before anyone can use these models in practice. So what I'm going to talk about today, how we handle each of these challenges in our ongoing work. Some are completed, some are still ongoing. So I'm going to show you some results, some progresses that we have made in each of these areas. Okay? So the first thing is real-world choice experiments. How do we design a real-world choice experiments to understand the effect of the decoy alternatives? So what we do is, in Singapore, the car prices are very expensive. So what we do is, generally ride-hailing drivers or even general passengers just rent their cars. They don't buy the car. So ride-hailing drivers also rent the cars. So what we do is we design a very interesting decoy experiment, which I'm going to talk about in a minute, to understand, can we introduce a decoy effect in the ride-hailing market so that the ride-hailing driver's preference can be nudged towards the electric vehicles. So what I'm going to talk about in this part, to handle this first part, how do we design the real-world experiment for the decoy effect, where we actually work with the ride-hailing drivers, not the lab students or anyone else. So I'm going to talk about 4 things. How do we design the experiment to capture the decoy effect in the real life? Then whether decoy effect is effective in the ride-hailing market or not. And why do these SSMs, sequential sampling models, outperform the utility-based models? I'll present some plots or some probability plots to explain why there is a reason that these SSMs are able to capture these effect of the decoy better. And once you estimate the sequential sampling model, can you effectively design that decoy effect so that you can nudge the preferences of the people? So let's get started with the first one. So what we do is, first thing, we do this experiment in the lab as well as outside the lab. When we do in the lab, we record the eye movement of the ride-hailing drivers. And when we do it outside the lab, we intercept the ride-hailing drivers on the street and we let them complete the survey. And we take help from the market research companies. So the first stage of this experiment is, we first ask them, okay, provide us the details of your conventional vehicle. So we ask about their monthly renting cost, daily operating cost, and driving range with full tank. So daily operating range cost is calculated. We don't ask them the daily operating cost. We ask them the mileage and how much did they pay for their last fuel tank filling and all those information to compute the daily operating cost. Now, what we do next is, if we look at the electric vehicle, for the electric vehicle, we know their mileage, so we know their electric vehicle operating cost, and we also put the driving range that we have in Singapore for on an average the vehicles that are used in Singapore. So next, what we do is we ask them, okay, we first present them the 1.3 times of the renting cost, which is, let's say, 2100. Then we multiply this with 1.3, and we present them that monthly renting cost for the electric vehicle. And we ask them whether the electric vehicle is equally, I mean, what do you think about this electric vehicle, which has 1.3 times renting cost of the conventional car? So if they say that I will continue renting my conventional vehicle, then what we do is we switch this cost to the 1.2 times instead of 1.3 times. We reduce the cost. Then again, we reduce the cost to 1.1 times if even the cost is still higher. And we keep reducing until they feel that the electric vehicle which is designed is equally attractive to their current conventional vehicle. So before putting any decoy effect, we don't want that there is any bias between the existing alternatives. We want that these two alternatives are equally attractive to them. That's the reason we first design equally attractive alternative for each respondent. So this is designed for each respondent differently. What we call this, if you look in the attribute space, which is the driving range, daily operating cost, and monthly renting cost, in the attribute space, we call this line as a indifferentiable line. So what you see red is the competitor, which is our conventional vehicle. And the target, this alternative we call is target, which will be clear in a minute when we introduce the decoy effect, because we want to increase the adoption of this electric vehicle. And what we do is, now we are going to introduce another electric vehicle, which we call the EVB, as a decoy after generating these two alternatives to be equally attractive. So what we do next is, we keep them same, whatever they have obtained in the first part, and we introduce a new alternative, which is electric vehicle model B, which we call it as a decoy alternative. We don't change its operating cost, but what we change is we reduce the monthly renting cost slightly, but we reduce the driving range significantly, similar to your coffee example. Okay, so this electric vehicle model B is a decoy for electric vehicle model A, right? So we want to see, if you introduce this model B into this choice set, does the overall preference for model A increases or not? Okay, and we don't change the daily operating cost. So what initial results show, in the initial results what we see is, after introducing the decoy effect, the preferences for the target increases slightly, which is 45%. But in absolute terms, it's very difficult to understand what it really means. So what we compute is, we compute the relative share of the target. The relative share of the target is basically probability of target divided by probability of target plus probability of competitor. And competitor, remember, is our conventional vehicle. Target is that EVA, which is the equally attractive vehicle. So if you look at, in this case, if you compute this ratio, it's 0.45 divided by 0.5 plus 0.41, it is 0.52. If there is no decoy effect, then this value will be 0.5, basically. Okay. So as of now, we can see that there is a presence of decoy effect. We could nudge preferences slightly, but not so significantly. So what we do next is we look at the sample. We split the sample into multiple classes, and we look at this RST value for the different classes of the people. So based on the age and the working hours. And what we see here, for the younger people, the RST value is quite high, which is 0.7, 0.66, very significant effect. If you look at the class 3, its RST value is very low. That means there is no effect of decoy for this class. And we delve deeper into it, we figure out their response time is very low. They are just choosing whatever is coming in the way. So basically, they are very ICAV-oriented people or conventional vehicle-oriented people. So this is how we first look at how the decoy effect varies across the different group of people. Now, I will not go into all the models that we have developed, but what we did is we mainly estimated 4 models: multinomial logic model, MDFT, MDBS, and revised MDBS. And because these all MDFT, MDBS, and revised MDBS is we have revised this MDS model to incorporate some new things, which are not super important for now. But the main idea is we present the out-of-sample Bayesian information criterion and the out-of-sample PRST minus RST, which is predictive relative share of target and minus the actual share of the target. Okay. So if you look at this figure, this quadrant, anything which is in this quadrant, basically lower PRST minus RST and the lower BIC are better, right? So if you look at the class 1, which has the very strong attraction effect, right? So if you look at this part, which is MDBS, by the way, these bars are there because we try with 100 initial values. So this is just the confidence interval of the parameter estimates, not the confidence intervals, the variation in the mean of the parameter estimates across those 50 initial values. And what we see is in the class 1, clearly MDBS, the sequential sampling model, has the lower PRST minus RST and even lower BIC as well. But if you look at the third class, where there is no attraction decoy, if you look at this third class, where the RST value is 0.28, actually MNL is better in both BIC and PRST minus RST. So when there is no decoy effect, when the decoy effect doesn't affect the preferences of respondents, in that case, RUM models are still doing better compared to the sequential sampling models. But when the decoy effect is there, in those situations, RUM models, when there is a decoy effect, in those situations, RUM models do not perform well. But when there is no decoy effect, then RUM models perform well. Okay. Now, if we want to understand a little bit further, why does these sequential sampling models really work better? So what we do is we sort of create the, let's say this is, we plot the driving range and again the monthly renting cost. And this is, let's say, target alternative, and this is somewhere your competitor, which is not visible, but here is your competitor. And competitor is your conventional vehicle, which has the very high driving range and the low monthly renting cost, and this is your target. So if you look at target is target EV. So what we do is we create this indifference line for a given attribute levels, and we use the parameter estimated by the MNL model, and we introduce the different specifications of the decoy effect. These are called asymmetrically dominated decoy effect, AD1, AD2, and AD3 and AD2. So we don't need to worry about this, but this is just a type of decoy. What we are introducing in our situation is A4 and A5. These are the regular traditional decoy effects that we are introducing. So A4 and A5 are what we have in the experiments, and these are asymmetrically dominated effects. So we have the 5 points, right? What we do is on these 5 points, AD1, AD3, AD2, and A4 and A5, we try to present we compute the probability of target in all these situations in the attribute space, and we compute the PRST for them. So if you look at the probabilities of the target and the competitor and the AD3 or target competitor AD1, target competitor AD2, and here you have target competitor A4. So one thing you will see, the probability of target and competitor is not changing due to introduction of the A4, which is the property of the MNL, right? IIA. But you might argue, oh, maybe nested logic can work better. So there is a paper by Angelo Guvera. I don't have that paper here, but they have tried multiple different substitution effects by changing the different substitution effects, but they are not able to capture the effect of the decoy on the PRST properly. But at the same time, for the similar configuration of the AD1, AD2, AD1, AD3, AD2, and A4 and A5, A4 and A5 are our decoys. So if you look at the A4, the operating cost is relatively, the difference in the target and the A4 operating cost is quite low. But so A4 is sort of not so strong compared to A5. So we see that if you look at the probability of target and the competitor, we see that they are not symmetric as we have in MNL, and we can clearly see that introduction of the decoy increases the probability of target for A4 and A5 compared to the competitor, right? So by looking at the PRST in the attribute space, you can see that introduction of the attraction effect really increases the probability of the target. Okay? And once you have this target, once you estimated the model, what you can do is you can try different specification of the decoy and see how that affect the preferences. So what we plot is for each respondent, we have the equally attractive alternative. What we do is we introduce the different decoys, where we decrease the driving range from 25 to 200 kilometer for the decoy alternative. And these different color lines represent how much we decrease the renting cost. And we can see that the renting cost is not affecting the PRST much, but the driving range is. So what it really means is that the optimal range of the decoy, if we really want to introduce the decoy effects, is around 50. So we need to reduce the driving range of the decoy by 50 from the target alternative, and we can just reduce the operating cost by 120. We can still generate the effect and increase the preference for the target. I'll skip the description of this plot for the time constraint. So this paper has a lot of details. I just made the main points. So we have just made the working draft public recently, if you want to get the details of the paper. Okay. I'll share the presentation slides as well. So the second part, how do we define the value of the response time? What do we learn from the response time itself? So one thing that we have already seen is the choice response time model, where we define the probability of choosing choice I and the response time P. This is we have defined in MLBA. But another new probability functional form we define is the RTG, which is probability of response time given choice, or probability of the response choice given response time. This is the new probability expression we define in this case. And the third one is the probability of just choice in these models, is we integrate out the response time in the joint choice response time decisions, right? So these are the three potential expressions that can happen when we talk about the joint probability or the marginal probability of choice and response time. So this is the new one. So what we do is to demonstrate that when you add the response time to the model, we show that this P underscore CRT, which is when you consider the choice response time, we first develop the asymptotic theory, and we show that these three different models, the estimator of these three different models asymptotically converges to the true value. And this way, we find the sampling distribution of all three estimators for MLBA first. Once we find the sampling distribution, once we find the asymptotic sampling distribution, what we do is we use the chain rule on the Fisher information matrix. And after using the chain rule means that if there is a joint distribution, if there is we have the theta corresponding to xy, then we can break it into x conditional on y and information matrix for just what we have conditioned on. Okay? So if you look at the CRT, which is the choice response time, we can then break it into the choice and the response time given the response choice. And similarly, CRT, this is the choice response time, we can also break in terms of the response time given choice, response choice given response time, plus the information matrix of response time. So given that we know that these two terms are positive, we can write that the Fisher information matrix for the CRT, which is a choice response time, is higher than the choice only and the response time, response choice given response time. What it means is if you estimate any model, the standard errors will be lowest for the choice response time model. And we show that through simulation as well. These are just different parameters, but one thing, what you see here is CO is the choice only model, CRT is the choice response time, and RT is the response choice given response time. Okay? So if you look at the CRT for all parameters, right? And you look at its confidence interval, right? If you look at the CRT, its confidence interval, its standard errors are always smallest. And we show that mathematically and through simulation. So what we are saying is there is a value in modeling the response time and choice together. But the new estimator that we have obtained, the response choice given the response time, if you think about the coverage all the time, it doesn't miss the true value. This red dot is the true value. This response choice given response time always include this true value, even if it has the larger variance. So we haven't proved this thing theoretically, but this is mainly finding from the simulation that response choice given response time has a higher asymptotic variance, but it has a very high coverage when it comes to including the true value in it. So that's the beauty of the response time given. So what I'm trying to say is that there is a value in response time theoretically. So there is a reason that we should include the response time along with the choice that we are getting. Third part. So the third part is the high dimensionality of the neurophysiological data. So this is the experiment in the lab that we have conducted. I told you that we have conducted this experiment in the lab as well as outside the lab. So when we conducted this experiment in the lab, we collected the eye tracking data, which you can see how it looks like. And it's a high dimensional data, right? And it is, if you look at this plot, you can see that these are people have spent more time on these attributes, but not so much on these two alternatives compared to the EV model A. So there is some element of attribute non-attendance, how people are processing the information, right? So what do we do to account for this eye tracking data in the MLBA model? So because it's a high dimensional problem in terms of eye tracking data has a trajectory data, so we have to find a smart way to account for this eye tracking data in the MLBA model itself, right? So if you look at the data set, we have the choice response time data, we have the demographic, and we have the eye tracking data. If you look at the input and output, input basically in this case we have non-informative priors. If you are doing with the Bayesian estimation, generally these models are estimated through Bayesian approaches. And one more thing we are getting from eye tracking data set is how the attributes are compared on each alternative. This is what we can obtain from the eye tracking data set. I'm going to talk about in a minute how we get this W hat Kij. So what we do is, if you remember your MLBA, it has this W hat Ikj, which is the weight which is given to the pairwise comparison of the attributes. We obtain this information from the eye tracking data. Okay? And once you estimate this model, you get the posterior distribution. So let's see how do we get the eye tracking data. So if you look at the eye tracking in the sense of three attributes and three alternatives, there can be three movements possibly. One is the within alternative-wise comparison, which are these movements. Within attribute-wise, attribute pair-wise transit, which are these movements. And then there is the other transit movement, which is this movement, right? So you can categorize all the movements into these three movements. So what we thought is it's not super easy to just look at how much time people are spending on an attribute and compute the probability, compute the pairwise comparison weight. it's still at the initial stage, but what we do is, it is not that if person go from A2 to A1, they have only compared this A1 and A2. Because they are going from A3 to A2 and then A2 to A1, A3 is still in their memory, right? So there is a comparison between A3 and A1 that might be happening as well. To account for both comparisons in the working memory and the actual direct comparisons, we say that the W hat Kij is basically probability that Xki and Xkj both are noted by the subject. Here we use the independence, which is not a very good idea to do, but we thought like let's start with the independence between these two, because once we do the independence, this is the information, the probability of Xki is noted by the subject or Xkj is noted by the subject, that is directly obtained from the data itself. So let's say this is the attribute level attention. This phi ki and phi kj is nothing but the attribute level attention. And once you use the attribute level attention and you plug in here, you get the W hat Kij, which is the basically probability of pairwise comparison of the of the two attributes, or two alternatives on an attribute. Okay, so this is how we get this W hat Kij and plug in here in the drift rate of the MLBA. Sorry, it's a lot of information, but the main idea is are simple, and maybe we focus on the main idea as we move forward as well. So the next issue that we had was the small sample sizes, right? Even if we have the attention weights, we just have the 40 respondents, and it's very difficult to estimate the model with the 40 respondents. So what we do is, let's say this is the lab-based data, and as I said, we get W hat Kij from the eye tracking data. We plug it into the MLBA model. What we do is we do the same thing for the online data, which is the data that we collect through the street intercept survey, right? But if we want to apply this model, we don't have the within attribute pairwise attention weights, right? We don't have it for the online data. So what we do is we do two information sharing process here. One is because we have the good posterior distributions here, we use them as informative priors in the lab-based data. Second thing we do is we transfer the attribute-wise, pairwise attention weight information here. And how do we do that? We actually use the demographic mapping of the attention, mapping of the demographics with the attribute pairwise attention weights, and use that mapping to compute the attribute-wise attention weights for the online data. And it apparently works well so far. Instead of demographics, you can use the attitudes as well, that people with similar attitudes focus on the similar attributes. The idea is along those lines. But before doing this information processing, what we also do is we look at the similarities between the lab-based data and the online data. So if you look at the distribution of the response time, this is pretty similar for the each choice situation. And if you look at the sum of the attitudes, like saving operating costs due to renting electric vehicle, or chargers in neighborhood areas are sufficient or not, whether these are the big concerns or not, if you look at the proportions across in the lab data and online data across different groups of the ride-hailing drivers, they are quite similar in the lab data and the online data. So this check is important before we are transferring any information from the lab data to the online data. So if we look at the two steps process, one is just transferring the priors to considering the posterior of the lab-based data as a priors for the online data. And the second step is transferring the eye tracking information itself. So if you do nothing, if you use the non-informative priors and no eye tracking, your posterior mean predictive accuracy is 60.556. And if you just use the informative priors from the step 1, which is the basically posterior of the lab-based data, the predictive accuracy increases. And in the sense, apart from informative priors, if also use the eye tracking data, the accuracy even further increases. 5% is not small if you think in a practical setting. 5% improvement is significant. But these are very initial results. It's still like a work in progress. We are refining our eye tracking formulations. We are thinking more about how do we better transfer the information. But the initial results are promising. So this is more about how we can incorporate the eye tracking data in the sequential sampling models. Now we try to think about a little bit about the brain data as well. What do we do with the brain data? So, because brain data is also very high dimensional. So we did a very interesting experiment. Maybe you already know about this problem. It is called the ethical decisions in autonomous vehicle. It is called the trolley problem. So in the trolley problem, there is this guy in the green sweater, and this trolley is coming on this rail. Okay. This guy has the power to change the route of this trolley, and if this guy changes the route of the trolley, it only kills one person, right? But if it doesn't, then it kills a whole family, right? So it's a dilemmatic situation, what this person should do. And there is a very famous paper, it is called the Moral Machine Experiment in Nature in 2018, where they show that this is the problem that we are going to face in autonomous vehicle world, and there are biases in the society in terms of which demographic group should be saved by different demographic groups. So the research question that we try to answer in this case is, can brain data help in identify the appropriate approach to collect the social attitudes in moral decisions? So we conduct this experiment in the picture-based experiment and the video-based experiment, which I'm going to show you in a minute. And how do we incorporate then the brain data into the behavioral models, which is a very difficult thing to do, but I'll show you some initial results which are quite promising. So this was the experiment. Let me show you. So you can see the vehicle is coming from the front and two pedestrians are coming from left and right. And this respondent is deciding which pedestrian is deciding the lane of the vehicle which is coming. This respondent can only save one of those two pedestrians. Let me run it again. So respondent just changing the position of the autonomous vehicle which is coming. So respondent decided to kill this pedestrian. Actually, there is a noise as well which happens when the pedestrian is hit, but I have muted the computer right now. So this is the experiment that was designed by undergraduate students, and we collected the EEG data along with it. So we have the 40 participants. We do it with the NUS students because it's a general experiment. We don't need the staff and the students, but we make sure that we have 20 participants, male, 20 females. And okay, one more thing before I go to the sample. We do the same experiment in the picture-based scenes as well. So we show them this situation, and we show them after situation, option 1 and option 2. In option 1, this left pedestrian is dead. In the option 2, the right pedestrian is dead. And we ask them to make a choice. Okay, so each respondent actually do 32 picture-based experiment and 32 video-based experiment. And we randomize the text and the video-based experiments as well, as in that 20 respondents do the video-based experiment first, 20 respondents do the picture-based experiment first. Okay. So what are the main results? So it's very interesting to see. If you look at the picture-based experiments, first, if you look at this plot, it is the gender of the pedestrian is on the x-axis, where you have the male and female. On the y-axis, you have the probability to save that pedestrian with the specific gender. Okay? And what you see in the white dot and the black dot is the gender of the respondent. So if you look in the male and female group, both wants to save females pedestrians more in the picture-based experiment. It is true in the video-based experiment as well, but females are a little bit more biased to save the female pedestrians, okay, in the video-based scenes. So we delve further into what's going on in this situation. Can we model this data through sequential sampling model? Does the brain data gives us some information about why this bias is happening in the video-based experiment? So what we did is, so in any brain data, we have basically different frequency bands. And the three most popular frequency bands are theta bands, beta band, and alpha bands. So we try to look at, are there differences in the frequency bands of picture-based and the video-based experiment. And we found that there are some differences in the video-based and the picture-based experiment. The video-based experiment has lower ERSP in the theta band, and same for the beta band. After that, what we did is we see that there are some differences how people are processing information in the video-based and the picture-based experiment. So we looked at the basic regression in the beginning, and we regressed the choice bias with the ERSP of the beta, alpha, and theta, which is just the frequency bands, ERSP in these frequency bands. And what we find that if you look at the significance, only the beta band is what was explaining the choice bias. Others were not significant apart from gender. Gender is anyway has a different choices in the video-based experiment. So so we see that the beta band has some information about why people are making different decisions in the video-based experiment. Now we went one step further. What we did is we developed a drift diffusion model, a type of sequential sampling model, and try to look at, you remember in the sequential sampling model we have 4 parameters: starting point, drift rate, threshold, and one more parameter. But so we created a traditional sequential sampling model. As I said, you can develop any sequential sampling model on your own. The structure should be same. So we created a sequential sampling model to reproduce the response time and the choices in these experiments. And what you saw here was the observed choice shares, right? Observed choice shares for each gender, basically to save each type of pedestrian. But what you see here is the predicted by the model. Model is able to replicate the actual response time that we have seen and the probabilities. So one thing which is interesting to see is among all 4 parameters, the non-decision time, starting point, we didn't see any difference between the male and female respondents. But the difference that we have seen was in the drift rate. So what we found that the female have the higher drift rate compared to the male, even in the picture-based experiment, but this difference become quite substantial in the the video-based experiments. Okay. Now we want to understand this further. The one thing which is clear that they are not biased when they come to the experiment. The bias happens when they are accumulating the evidence. And that means that the form of the experiment makes a difference in terms of what people are responding to. So this is clear that the bias is not inherent, at least in the sample that we are analyzing. The bias is developed during the evidence accumulation process. Now we did one more interesting thing here. What we did is we look at the beta band, which was explaining some of the choice biases. So interestingly, if you look at the ERSP of the beta band and the drift rate, you see that the drift rate is higher for the low ERSP beta band. Basically, beta band is negatively related with the drift rate. That means positively related with the negatively related with the bias as well. So if you look at the beta band ERSP, you can see that the one has the low has the high bias, which is corresponding to this. So what we can say with this aspect is during the beta band ERSP actually explain the emotional response to the evidence accumulation process. So what we can say is in the video-based response, this emotional aspects are more easily occurred because the way the information is presented, and that causes the bias. So this closes the story down in terms of using the connecting the sequential sampling model with the brain data and also with the observed data that we do in the choice bias. Still, we are writing this paper, but and we are trying to develop more relations between the brain data, the results that we are getting from the sequential sampling model, and the observed choice biases. So the conclusion is, yes, response time is easily obtainable, and it can improve the statistical inference because you can improve the standard errors by just incorporating the response time. What we have seen so far, that these are all unexplored territories that we are touching, but the initial part that we have seen that calibrating SSM parameters with eye tracking and brain data is possible, because we have already seen that there is a relation between between the brain data and the drift rate. So if we parameterize the drift rate with the brain data, we might be able to do that very easily in case of this last experiment that I've shown. And the third thing is the fusing the lab data and online data is a way forward if we really want to use this eye tracking data set and the brain data, because otherwise the sample sizes are too small. And I haven't discussed this part, but we are also working on developing some computationally efficient estimators to estimate these models, because these models are very hard to estimate. So we are developing some variation inference-based methods to estimate these models. And finally, we are exploring the new ways to collect the eye tracking data. These days, even the computer's webcam can be used for collecting the eye tracking data. It's relatively new ideas that are coming up. We are testing the accuracy of it. We are designing the experiments so that we can compare our lab-based eye tracking and the web-based eye tracking and see its accuracy. So this is, I have written a kind of, I would say it's not a review paper, but it's just a piece to provide the perspective on where we are in terms of eye tracking research and what we need to do next if we really want to use the eye tracking in future in the behavioral modeling. So this is a paper which is still under review in the Journal of Choice Modeling, but you can read it if you are interested in this. And this is our LinkedIn page of the lab, which is very new, just started recently. And I'll just close after showing you, we have what are the facilities we have in the lab. So I can show you quickly the video of the lab. Maybe I can. That's it. Thank you.
Hi, Frank York here. This is the EMS foot massager. EMS is electrical muscle stimulation.
Oh, no.
It's low frequency.
Sorry about that. Yeah, I'm happy to take questions if you have any.
So as I understood it, you sort of start from this point of finding the point of indifference. And then you're looking at these pairwise comparisons.
Yeah.
In there, where in there are you able to, or is this sort of not yet there, back out sort of the relative weights of the attributes, right? It's because if it's, I understand the pairwise comparison, if one is clearly better than the other, but how are you extracting sort of the relative advantage of what's a good example in here, right? The, you know, operating cost and capital cost.
Right. So here, what happens is, if you look at the, so you're saying that why this MDBS can capture the decoy effect better, right? Where the pairwise comparisons are captured in any of these sequential sampling models, or more from the empirical perspective.
Yeah, I mean, I think often what we want to learn is sort of what's the relative value of reducing operating costs versus reducing capital costs.
We don't, the objective was not to provide the willingness to pay estimates, basically. The objective was to, how do we design the decoy which really increases the preference for the target alternative? So we don't actually compute the willingness to pay estimates in the whole paper.
No, yeah, and I didn't mean in your paper. I think I sort of understood, but it's like, is the framework amenable to that?
I think because RUM theory is not used, so willingness to pay estimates will not be meaningful if we use these models directly. So we can compute the marginal effects very easily, and we can convert those marginal effects into willingness to pay by marginal rates of substitution. But I mean, again, like you can do that, but it's not really a willingness to pay. It's just telling you that how people are trading off different attributes together. Same as like in the semi-compensatory models. You can still compute the willingness to pay estimates, but those are not really willingness to pay estimates because you are already assuming that people are not fully trading off the attributes. They might be partially trading off some attributes and partially trading off other attributes. I think when we are assuming the fully compensatory decision-making process in RUM models, then I think the marginal rate of substitution will be more meaningful to report. Yeah, that's the reason we didn't report that in this.
I guess this is kind of a simple one, but when you were evaluating like what the equal level of each alternative was to design the decoy, how did you decide to use the range as the?
So we looked at the companies who are renting the electric vehicles right now, and we look at the distribution of the range of the electric vehicles in the market. And we saw that the most range is 400 to 500 kilometers. So that's why we use the 450 kilometers.
But why range as the attribute instead of the operating cost reduction?
Yes, so why we did that? Because renting cost is something which can be changed by the operator. But the range is something that the operator cannot change. So that's the reason the change of the attribute that we allow respondent to choose is the renting cost, not the driving range or the operating cost. Because it's something in control of the operator.
Yes. Sorry, go ahead.
I was going to ask about like your inference strategy. So you mentioned like you might try to substitute variational inference.
Yes.
So did you present on the likelihood function? Maybe I missed it.
No, we are using the differential evaluation Markov chain Monte Carlo estimation right now. Traditional Markov chain Monte Carlo doesn't work very well for these models because they have some correlation, inherent correlation in the parameters of the models. So you have to do some of the ensembling when we are estimating the MCMC. So we start with multiple chains together and we do some swapping like we do in the genetic algorithm. So that's why it's differential evolution MCMC, which is what we are using now. But we have tried that the variational inference also works very well if you're not worried about the standard errors of the parameters. But as a first estimate, it's very fast and it's a useful strategy to estimate.
And there's like no way to formulate this in some closed form, right? You have to simulate it.
MDBS can be done. So we have done the likelihood-based estimation for MDBS, choice response time. It works well. But not for MDF BFT choice response time, not for MDBS choice response time. It's a bit tricky. Yes, Don, you had a question.
Do you see any possible extensions? Again, I think you've got your face-to-face data that you're using. Do you see any opportunities to sort of extend this to like browsing history?
Yes.
Or something that you could apply at a larger scale?
Yes, it can be incorporated into the recommender systems. Basically, in the Amazon or other places where people already are choosing, let's say, two alternatives. We introduce the third one as well there while we are recommending to the product. And there, how do we design the third alternative attributes? There, these models can be very, very useful. So we are exploring those possibilities with PNG right now a bit. We had done some work with Nestle, but not exactly applying these models. But we saw that the FMCG companies are very interested in using these eye tracking data sets and the brain data because they're more interested in food packaging as well. That's another area that they are interested in. But certainly the recommender system is where they can be practically used in terms of, especially how do we design these decoy effects, that thing can be very useful.
But in terms of so that's an application. Can
Yes.
you use those data to fit your model?
Oh yes, that data can be used if we know the equally attractive line, because otherwise it will be a bit biased. We have to think differently if we are not able to create the equally